Welcome back to Cloud Computing and Big Data. Today we have our lecture 11, and I'm pleased to have an invited lecture today by PhD student Chadi Barakat, talking a bit about big data analytics and cloud data mining. Chadi, can you introduce yourself a little bit, what you're doing?
Yeah, thanks, Morris. My name is Chadi Barakat. I'm a PhD student from Lebanon. I'm doing my PhD in bioengineering in Iceland, in a part of the group that Morris is heading. My PhD work is mostly in the medical field with applications of machine learning, deep learning, data mining, and data science for the improvement of ICU and diagnosis of mostly what I'm focusing on is diagnosis of conditions that affect ICU patients, respiratory conditions specifically. So my work is mostly divided between Iceland and Germany right now. Germany at the Jülich Supercomputing Center, but also with in cooperation with the University Clinic of Aachen and other medical institutions in Germany. But in Iceland, I'm mostly also part of the simulation and data lab for health and medicine, which Morris established, and I'm a founding member, I guess. With that, I guess that's mostly all of the work I'm focusing on for now. What the future brings, we will never know, but I'm open to looking into more applications of big data analysis and machine learning, especially mostly in healthcare.
All right, yeah, thank you very much, Chadi. Before we go into the material of big data analytics and data mining, perhaps we should review what we had the last time in lecture 10. If you can just move to the next slide. Exactly. If you remember, we had last time basically introduced this interesting SAAS term, which is now the software as a service, which is basically on top of all of the stacks that we had before. So we had infrastructure as a service, talking about virtualized servers, storage, data centers, really the physical data center perspective, a little bit what you have seen at our visit at the Borealis data center, right? So this was really pure infrastructure considerations. Of course, along these lines, there goes some security aspects, networking, which was also an important part. You have seen all the cables in the Borealis data center. So on top of that, you have often this platform as a service, which then extends, of course, the idea of these pure infrastructures with some added value building blocks. You remember we had the Lego analogy where we said, okay, for developers, we need here and there some Lego blocks always to create interesting applications. That could be a billing module, could be a monitoring module if the system is quite well running. And we have also seen that, for instance, in the Google space of the cloud, there's a real support for the whole development cycle of apps, for instance, which of course is an important part, different language support, different version support, etc. So PAAS was really the perspective of the developers, and then last time we really extended this to the view of clouds to have just applications. Needless to say that they build usually on the platform as a service and infrastructure as a service models, but of course are really abstracting everything away that you see on the right-hand side, which is rather the infrastructure and the platform, focusing completely on the application. And of course, you use them daily, right? SharePoint, Google Docs, it's what we discussed, but also very specific ones are existing that some of you may know and heard of, which was the CRM applications. We looked at a few like Zoho, for instance, where basically we had seen that this is a really interesting cross-selling opportunity in clouds, making this software as a service so basically so successful today. Because basically when you do CRM and you basically subscribe to it, as you know, I call it the swipe the credit card, then you basically have bought this very easily in the cloud. You have access to it, and suddenly you require a marketing campaign module, and it's just next door. Or basically you want to have an email campaign, it's also next door. So basically lots of different applications around, and the same is actually true for Freshworks, for many other basically applications in the cloud. They make heavily use of this cross-selling idea that just with 1 or 2 clicks, your credit card is already there. So you basically can extend the services to another module or to another part of the application, and basically linking it back to our ideas with machine learning in the course. Amazon SageMaker, the one that you also have in your assignment, is a very good example of this idea of SAAS, where you have a fully, let's say, managed environment for machine learning. And then also you have seen in the CRM, for instance, a module intelligent assistant, where you basically have an AI-powered assistant to check with sales, to check with your customers, so that you can, of course, with another click activate, and here you go, you have, of course, to carry the costs, right? So this is, of course, a good business models for the cloud, especially as we said in the course, compare it to moving to some real shops and buy the software there. So everything is online, everything accessible. And I think with this, I would say I close here and give back to Chadi to cover now new interesting perspectives of how we use cloud computing, basically with big data. Here you go, Chadi.
Yep, thanks. Thanks again, Morris. So just before we move along with the lecture for today, I just want to point out that if you want to get in contact with me, my social handles and my email are here on the title page of this presentation. I'm sorry I couldn't be there in person today because I would have loved to get some feedback from you, or some questions, and maybe do a question answer round, but I am available by email or over LinkedIn if you need to contact me. So the lesson today is mostly going to be about big data analytics and cloud data mining. And to tell you exactly how that works, I'm going to show you some of the practical examples that I'm working on right now and I've worked on during the 3 years of my PhD. So just not to take too much time, let's just dive into it. So in this lecture, it's going to be divided into 2 parts. It's going to have the first part about association rule mining in big data, which is one of the projects I worked on at the beginning of my PhD. It doesn't have a lot to do with medical applications, but it helped a lot set up the groundwork for data analysis for my future applications. The next part of the lecture will cover data mining and deep learning for healthcare, where we go through a short refresher of what deep learning is, and then go through the details of what kind of work we're doing with 2 prime examples of what I'm doing right now that explain exactly where these applications come in and why data mining and data analysis is important in this case, but also where these applications kind of take advantage of the available cloud computing resources. So let's start ahead. Association rule mining in big data is something that you hear about a lot, or if you haven't heard about it, you've experienced it a lot. So association rule mining is basically the concept of collecting information about purchases from a lot of people or from specific people, and in order to improve the recommendation systems for future sales. So in this case, it's used for, let's say, when industry or shops or online stores collect all of the sales information that they have and then allow data analysts and data scientists to look into that data, there are some unknown relationships that maybe come out or stand out from these sales. We'll go into the details of that in the next slide, but mostly this information is relevant to improve sales, but also it's such a broad spectrum of information that one person alone or 100 people sitting at a desk for 24 hours for years are not enough to extract this information. And this is why association rule mining is mostly a machine learning application, or it's a computer-based application of this of data analysis, where the information extracted is very large, but also very informative. So by making it automated, we can extract this information in a much easier way. The approach for it is mostly an unsupervised machine learning application. So unsupervised in this case means that we just give information and let the algorithm do its job. And then we tell it if it did a good job or not, and then repeat. There is no extra input given from our side. And for association rule mining, there are several approaches, several algorithms that exist, and each of them is adapted to specific situations, or they are just evolutions of the original algorithm. We'll talk about a priori versus FP growth in the coming slides. But mostly the concept of association rule mining is all based on one famous example, which is this one. So it's the shopping cart experiment, where we look at what people buy, and then we try to extract information from it. This is a very simplified example, of course, but you can see here that in all of, let's say in these 5 transactions, we have diapers and beer appearing a lot. So it tells you a lot of information about recent parents. They can't go out to the bar anymore, or they can't go out with friends. So they are more likely to stay at home, but they still don't want to miss out on the alcohol, for example. So they buy beer, or probably in bulk. So the algorithm in this case would learn that, hey, maybe if this person is buying diapers, let's recommend beer. They are likely to want to buy it based on this information. And this illustrates exactly how these relationships are extracted from the available data. But the data needs to be clean, the data needs to be accurate, the data needs to be well prepared, and that's usually a problem with transaction data from retail. Sometimes the people don't label things correctly. Sometimes the same thing is labeled 4 different ways. We never know. So it has a lot of challenge, and as it's mentioned here in the text, like there are data sets that have billions of transactions, and data cleaning is really not the most fun job to do. Sometimes you just have to come at it with an axe. So it has its ups and downs, and so for that reason, algorithms have been developed to do the cleaning, and algorithms have been developed to do the association rule mining in the first place. The automation of this process is very helpful, but also automation in this case is still based on maybe serial applications and not parallel applications. So they don't necessarily take advantage of the growth that can happen with parallelized computing or with cloud computing resources. So the hook here is that we need to take advantage of these algorithms that are efficient and that grow well with the data, but also we need to take advantage of resources, cloud computing or high performance computing resources that are available in order to accelerate this data, this automation or this data processing. Because as I said, we have billions of transactions. For example, an Amazon transaction list, they have billions of transactions per day. So the algorithm for Amazon, for example, might be working correctly. It might also be working on this standard here, but it takes advantage of the services that they have at Amazon for the web hosting and for the shopping thing that they have. So it takes advantage of the available resources in order to scale it up and accelerate this transaction, this association rule mine. The project that we were working on, Morris and I, was the On for Off project, which was a project for German retailers, trying to bring them into the internet. So these are the small shops or large or medium to large businesses that have not had access to online resources, have not taken advantage of the internet for their sales. They only take advantage of like the over-the-counter and like brick and mortar shops. So the goal of the project was to introduce them to the internet and also to introduce these internet resources and algorithmic resources to the shops themselves in order to improve their sales. And that's why it's called On for Off. It's the application of online resources for offline sales. So they had a lot of a large amount of data available in terms of sales and in terms of like rebates, discounts, the types of customers they have. Also, they have like the customer loyalty cards, where it collects more information, more specific information about specific customers. So all of this information is very useful, but they weren't taking advantage of it much. Mostly it depended on the salesperson at the store recognizing this customer and then just like trying to upsell to them. But that person will know 2, 3, maybe 4 connections at max in terms of like this product and that product. The algorithm maybe can take advantage of these the association rule mining that we talked about before and extract more relevant information, maybe recommend things that no one in their right mind would have thought about. So by applying this to these stores, maybe we can improve the sales. Maybe it's just something that's a social experiment. But it specifically became necessary, or became evident that this is necessary during the COVID pandemic, because all of these brick and mortar stores had to close down and they had to depend on the online sales. So it was a clear reminder that being online, being able to recommend things to customers locally, offline and online, is a major thing that they need to be working on. And that's where our work was very helpful in this case. So the algorithms that we're going to talk about today are mostly the association rule mining algorithms are, first of all, the a priori algorithm. And then the next one we'll talk about is the FP growth algorithm. But a priori is mostly the most basic example of association rule mining, where if you have a transaction, a list of transactions, the algorithm will go through that list of transactions and make a list of how many times every item in that list appears. And then it trims away any item that doesn't reach a threshold. So that threshold is set as, for example, here, I think it is set at 2. So any item that has 2 or less, appears 2 or fewer times on the list is removed. And accordingly, any collection of items that has this item that doesn't reach the threshold also doesn't make the cut, because, well, it has that one item that isn't famous. So anyway, any combination of items, including this one, is not going to be famous or is not going to be popular. So from that first list of, from that first reduction, the algorithm passes a second time for each of the remaining items. For example, in this case, we take beer. It goes through the list again and looks for all of the places where there's beer and tries to see what items appear in it. So it's beer and bread. Here we have beer and bread, beer and diapers, beer and eggs. Beer and cola doesn't count because we already established that cola doesn't really reach the mark, so we ignore it. So that's why we have here beer and bread, beer and diapers, beer and milk. And then the next one is bread, and so on and so forth. And again, here we apply the same filter as we did in the first time. And any items that don't reach a minimum support, which is the technical term for it, this minimum support of 3 is not reached here. So this item is axed and this item is axed. What remains are these 3 connections here. From these 3, we also expand a third step. That's a third time that the algorithm runs through the whole data. And you can start seeing where this might be a problem. It goes through the data a third time, maybe a fourth time, maybe a fifth time, in order to extract the most popular item sets. In this case, it's a 3 item sets that has bread, milk, and diapers. So every time you see bread, milk, and diapers, these items are regularly being recommended. This here is a very strong connection. For example, bread, milk, and diapers are common things that people buy all the time. But this doesn't tell us much. This tells us, okay, this is the most famous item set in the whole data, but it doesn't tell us what are the things that we wouldn't normally conceive in a normal situation. This here is a bit informative, but at the same time, not very useful in case it doesn't reach the minimum support. But anyway, the a priori algorithm extracts these item sets and applies some calculations to it in order to provide the recommendations. These recommendations are based on some support, but also based on confidence and like the main features of accuracy, let's say. They are confidence. They tell us about the value of the prediction that the a priori algorithm is doing. So these values are confidence, lift, leverage, and conviction. And you can understand from at least confidence and conviction what these values mean, how confident the algorithm is that this is a valid connection, and how and the conviction in that this is useful. So in this case, we have the actual data set that we were working on. This is a reduced part, but this is still kind of relevant. And you see that in this case, we are talking about support, minimum support of 3 or 4 or 2. But when the data set gets larger and larger, when you have 100,000 items that you're selling and 1 million transactions, you might not even have a minimum support of 1. You have to get smaller and smaller. So, because you're going through all of the transactions. So in this case, Hugo Boss, for example, has one of the highest support. No, actually, Armani has one of the highest support at 0.7, close to 1, and that's just unheard of. A lot of, apparently, Armani is quite common sold in those transactions. And from there, like the item sets, as we've mentioned here, 1 item sets, 2 item sets, and 3 item sets are generated through the a priori algorithm, and then the association rules are generated. The thing with this is that we are applying a specific algorithm developed under the MLExtend library for Python. The MLExtend library has also other applications of machine learning and association rule mining available. But in this case, we're just setting a baseline of what an algorithm should do. And using a priori in this case was very, very resource exhaustive, to the point where sometimes the value stored in memory was about 300 gigabytes. Or was it 30 gigabytes, but still, like, it's an unreasonable amount of data being stored online. And we had to think in parallel in order to have this online, because even the high performance computers at Forschung Centrum Jülich weren't up to the task of holding that much data in memory, because the algorithm, as I said before, has to do several runs through the data. That means several runs. In this case, I mentioned that it ranges from 1 to k minus 1, and k is the total number of unique items. So if you have 40,000 unique items, you have 40,000 to the power of 39,999 amount of information. Even if it's just like zeros and ones, it's still going to be a massive amount of data. So you have to take advantage of the resources you have, but also you have to be smart about it. So for a priori itself is a very good algorithm to show as a proof of concept of the whole idea of association rules. The only problem with it is that it does not scale very well. There have been several approaches to parallelizing a priori, but the alternative is a lot better, so there's no point doing it, I guess. It's very good for small number of transactions, like maybe a small store that doesn't have many branches, but still maybe at that point it will be crippled a bit by the amount of data that it can generate from the available information. So like I mentioned before, because it takes a lot of passes through the data set, every step decreasing the number of items by 1 or by 5 or by 100, it still has to go through a lot of data and it has to store them. And if you do not have enough storage, you cannot do this. So it always helps to be able to know what kind of resources you have and what kind of problem you have in order to be able to solve this problem in the most efficient manner. And we'll get back to that in the second part of the lecture, where we talk about the CRISP-DM model for solving machine learning problems. But until then, we move on to a more efficient algorithm that was developed also based on these transaction information. This model is called the FP growth algorithm, and it also does the same first approach as a priori, where it goes through the data for through one pass. In that first pass, the FP growth algorithm doesn't just collect information like repeatedly passing through the data. It just does one pass where it collects information about all of the available items one time. And then the second time, it tries to build a kind of tree where it makes internal connections instead of just trying to make every single possible connection. So in this case, you can see that the frequent pattern tree, which is this tree shape that we have at the end here, starts with the null point, which is that no items are being selected, and then, for example, A. And every time it sees A in a transaction, it adds a point to it. But from there, it starts to build. So it's A, B, and C, and D. And then A, B, and D only. A without B just continues to C. But these add together. The C's add together. The B's add together. So in this way, the algorithm only has to do two passes through the whole data in order to make all of these connections. It's just trying to collect as much information as fast as possible without having to overload the memory with information that's irrelevant. In the end, like any information that was being collected by a priori might be irrelevant. We're going to axe them, so why collect them in the first place? And this is where FP growth kind of provides an improvement over the a priori algorithm. Essentially, applying FP growth is exactly the same as applying a priori, using MLextend in this case. We applied it to the data we have. And the picture here highlights the speed up that can be achieved using FP growth versus a priori. In this case, running it on here, running two instances of a priori for data for association rule mining versus one application of the FP growth, and the amount of time required for running the same task on the same data is halved. And as you grow in terms of, you can see here, as you grow in terms of the data that you have, the FP growth still takes a bit more time to do this as the data grows, but it doesn't scale in terms of time and resource usage as much as a priori. So this makes it very adaptable to large-scale data sets. And in our case, that was very helpful, being able to generate the frequent item sets and the association rules for the data that we have. Using FP growth on it was very helpful, especially with the fact that FP growth isn't trying to actively kill the memory that we have. So it was very helpful applying it, and also it was very informative because the fact that it was able to do this without us interfering with the data meant that we aren't introducing any further bias into the data. So we're not cutting it in places where it might affect the quality of the data. So as an example of this being applied through cloud resources, we have the IBM Cloud Pak for Data, which has built-in association rule mining applications. And this is a fully integrated data and AI platform where you don't really need to install anything on your computer or on the customer's computer or anywhere specifically. It's just available online, and I think for a subscription service, it's pretty good. We also highlight here some other resources that I think that will become useful if you ever get into this field. But mostly lecture 12 will provide more detail about all of these things and also the applications of what's it called, of containers for these kind of applications. The SPSS modeler here is being is given as an overview, and you can see it also applies the CRISP-DM. But these are applications of what's called of association rule mining, for example for retail. There's also this example about applications of the algorithms that we just talked about, FP growth here, on Apache Spark. This is a follow-up for lecture 2, and it's interesting that this stuff is also available on Apache. So like, it tells you a lot about how important this algorithm is and how necessary it is to use it, and to the point that it was also applied to these cloud resources. So with that, we get to the end of this section of the presentation, and I just want to mention that we are talking here about applications in retail, but if you think about it, medical data, for example, applications of collecting data from patients, where you have the blood pressure, blood sugar levels, oxygen levels, CO2 levels, any kind of information from the blood that you extract from the patient, can be also seen as this kind of data, this transaction data, for example. And you can see that all of these, for example, if you replace bread, diapers, beer, and eggs here with high blood pressure, low blood sugar, diabetes, and then heart attack, you can start seeing that, okay, these things come together to cause that, and association rules can be extracted from this as well. Which is why working on this project was very interesting for me, because it allowed me to think of all of these problems in a different way. And you, as people who will work in the future in this domain, it could be an application in the medical field, or in satellite images, or in ground coverage data, or in transaction data like this. You have to apply the knowledge that you have in different ways, and that's where your intelligence comes into play, where you can look at the problem just like everyone else has looked at it, but also see it from another angle. For this purpose, I think taking these courses and knowing about this information, knowing about these algorithms, this transaction data, helps a lot try to get a different perspective on the problem that you're working on. So with that, we get to the end of this section, and we'll take a small break. And when we get back, we talk about data mining and deep learning for healthcare.